Hello, my name is Krish Gandhi, and this is Lab 3 Circuits. So, to start off the introduction of this lab, or the purpose is that we're basically looking at the principles of energy and current conservation to analyze electrical circuits in the experiment. So, this included ways of measuring the behavior of the circuits through series and parallel methods by looking at the resistors. We looked at the current and potential differences from the circuits and even examined the characteristics of ohmic resistors and capacitors. Fundamental principles. So there's Ohm's law, which is V equals IR. We did this to look at the voltage drop, current, and resistance. There's Kirchhoff's rule, which basically said the sum of all voltages around a closed loop is going to be zero, which is, so the formula is delta V equals zero, or the sum of it. And then there's Kirchhoff's node rule, which is the sum of the currents entering the node equals the sum of currents leaving the node. So IN equals I out. Okay, and here are some more equations. There's obviously Ohm's law equals IR, and then there's the capacitance formula, which is C equals Q over V, Q being the electric charge, V being the voltage. So summary of our results is, so on the right is two images of the circuits, and then we calculated the resistance. We used the wire, and our R1 resistor was 47, the R2 was 100 ohms, and the time to charge and discharge, they were not equal. The charging time was about a little over double that of the discharging time with 107 and 28 respectively. Okay, so the system in part one was the circuit, the surroundings was everything else around it. The procedure was we looked at two 1.5 volt batteries connected in series and with two resistors. There was obviously R1 and R2, 47 and 100 ohms. And then we looked at two ammeters, which basically saw the value of the current. So the first time we saw current one at 0.0208 amps, and the second time was 0.01997 amps. Okay, again, here's the image. There was the node rule and the loop rule with those formulas right there being implemented. Part two, the system was the circuit, the surroundings was everything else. The procedure, we looked at reverse ammeters and used 9V batteries connected in series with two resistors, and it produced 10 ohms of resistance light and zero point 0.2 farads for the capacitor with two ammeters. And the time to charge and discharge is about the same. Part three, there was no voltage drop across the circuit. It read -3 the whole time, and the batteries ran directly into the voltmeter with nothing to stop the current from reaching it. And then our ammeter is at zero in this case because of high resistance of the voltmeter. So what little current makes it through the voltmeter is going to be stopped by the resistors, and then all the other values are the same. Here's some code. There's a picture. Okay, and then some sources of error. Obviously, there's instrumental errors, connection errors, resistor tolerances, battery variations, and human errors. And then that's some of our calculations right there. So the discussion questions. So what if you hadn't oriented your experiment to compensate for magnetic north and instead just laid out a meter stick at some intermediate angle with respect to Earth's magnetic field? How would results change? So in that case, the magnetic field of the Earth would interfere, making all our magnetic field measurements inaccurate from the vector sum of the bar magnetic field and the constant Earth's field. So as a result, the distance dependence on the magnetic field would not follow the expected relationship, and it would lead to an incorrect fit. And then the second one, what if you were to stick two identical magnets together end to end and run the experiment again? How would they differ? So if you put them end to end, north to south, it would just act as like a single large magnet, and the result would be a magnetic dipole that's approximately double. And that's it. Thank you.